So last time we talked about this conversion from going from the little to the big picture. So we have a counting system now through Avogadro's number, which is represented by n to the subscript a, which is 6.022 times 10 to the 23rd atoms or molecules or ions, equivalent to a single mole of that substance. And so that's going to correlate at the large scale into grams of that substance based on the atomic mass or the molar mass. So we've already calculated our molecular weight or our molar mass of sodium bicarbonate. We found that it's equivalent to 84.01 atomic mass units. When we convert that to the big scale, essentially what we're saying is that there are 84.01 grams per mole of sodium bicarbonate. So, and we know that 1 mole is equivalent to how many molecules of sodium bicarbonate? That's right, 6.02 times 10 to the 23rd molecules of sodium bicarbonate are present in 84.01 grams of this substance, or 1 mole of this substance. So this becomes a very powerful tool that allows us to relate gram weight of different compounds to the chemical formulas that we've been writing to produce these different compounds. So you use Avogadro's number when you need to convert between the small scale and the big scale. Essentially, when you're looking to do reactions in the lab, reactions are written in the small scale, so you need to use Avogadro's number at that time and our concept of the mole to utilize chemical equations and mediate chemical reactions in the lab. So we could calculate how many carbon atoms are in 2.5 moles of carbon. So our goal is number of carbon atoms. So we know that we have 2.5 moles of carbon, and we know by definition that 1 mole of any substance has 6.022 times 10 to the 23rd units within that substance. So we can convert this, in this case our units are the atoms of carbon, so we can use this conversion to calculate the number of atoms that are in 2.5 moles of carbon. So we're going to multiply 2.5 moles of carbon. This is going to become our conversion factor. It's like multiplying this number by 1, right? Because 1 mole of carbon has 6.022 times 10 to the 23rd carbon atoms. Our moles are going to cancel out, and we're going to be left with our answer in number of atoms. So you do this calculation, and we would find that 2.5 moles of carbon has 1.51 times 10 to the 24 carbon atoms. So is that reasonable? It's a very large number, but a mole is a very large number, and we can see that it's much larger, significantly larger than our starting for 1 mole, and that's what we would expect for 2.5 moles of this substance. So it's very large, but it should be. So how many moles of water are there then in 3.01 times 10 to the 23rd molecules of water? So we can do this in the reverse then. So we know we're starting with molecules, but we know by definition that 1 mole of any substance contains how many molecules? That's right, 6.022 times 10 to the 23rd. So we can use this upside down in this equation to calculate the number of moles. So first we set our goal. We want to find the moles of water from our equation. We know that we've got 3.01 times 10 to the 23rd molecules of water. We can multiply this then times moles over 6.02 times 10 to the 23rd molecules of water. Molecules are going to cancel out. We'll be left with moles of water, which is our goal. And we see that this comes out to 0.500. Notice we've got 3 significant figures in our answer. We've got 3 significant figures in our question. So we've maintained our significant figures going through the equation as well. So is this reasonable? Well, we know that 1 mole contains more molecules than is shown. So this is below 1 mole, and so this is reasonable. So this represents conversions then to number of molecules using Avogadro's number. In the next section, we'll use moles to convert to the molar mass and relate it to gram weight.